Hello and welcome back. Today I want to continue talking about impedance matching by looking at how transformers can be used for this purpose. Previously I looked at how impedance matching can be achieved using resistive lossy circuits, but also using reactive LC network lossless circuits. Now both of these previous methods have their drawbacks. The resistive matching, although works in any frequency, will be lossy. Energy will be lost as heat on the resistors. And the reactive LC method is lossless. The reactive elements do not waste heat, but they only work under limited frequency conditions. So what makes transformer matching special is that it combines the best of both worlds, to a certain extent at least. It's a lossless matching method, it's made with coupled inductors, but it's also relatively wideband. So you can build matching circuits that work over multiple decades of signal frequency. Now, of course, you can make narrowband matching transformers, but today I will focus on the wideband applications. So if you're curious, then keep watching. Now, to start things off, an impedance matching transformer is just the same as any other transformer. It's made with some wire wound around the magnetic core, or an air core. You can have as many windings as you want, so you can match two or more impedances at the same time. And the coils can be separate or interlinked. So auto transformers are also used for matching purposes. Now, for an ideal transformer that has a specific number of turns on the primary and on the secondary, if we apply a specific voltage on the input, we'll get a specific voltage on the output, and then a certain current on the input and certain current on the output. And for the ideal transformer, we can say that our turns ratio is equal to the voltage ratio, and it's equal to the inverse of the current ratio. Now, just to keep things simple, this turns ratio we can also equate to a value n. Now, taking this relationship, we can extract a few things. So we can extract the relationship between the voltages and the turns ratio, and if we talk about resistance or load, we can express this as the ratio between voltage and current, so applying Ohm's law. And now coming back to our voltage to turns ratio relationship, we can replace this and create an expression in regards to the turns ratio and the impedances and currents. Now, regarding these currents, we can again turn back to our initial relationship and say that the primary current is equal to the secondary current divided by the turns ratio, and we can take this and put it into our previous equation. Now we can simplify a few terms and then move all of the n's to one side and all of the impedances to the other. So what we end up with is the relationship between the impedance ratios and the turns ratios. So what we can say is that the impedance ratios is equal to the square of the turns ratios. Or in other words, a transformer that has a turns ratio of 1 to 2 will generate an impedance ratio of 1 to 4. And of course, other values can be obtained with other turns ratios. Now you can check how well an impedance is matched to a signal source by using a circuit simulator. So we can compare a circuit built with a matching transformer to a circuit in which we have a signal source with a specific series impedance and a matching load impedance. So we can say that the load is matched to the signal source when two conditions are met. First of all, the signal that is present on the output of the signal source is half that of the no load signal. So this signal source has an amplitude of 1 volt, but if we run and check, it only has a peak amplitude of 500 millivolts. That's because the voltage is divided between the series impedance and the load impedance. And if we look at our second circuit with the transformer, we see the exact same thing. Secondly, we can look at what power gets delivered to the load. So we can look at the power delivered in the first circuit. We have peaks of 5 milliwatts, and in the second circuit we have the same thing. So both in the first circuit and the second circuit, the load is matched to the signal source. Now, the transformer that I used has a 1-to-1 turns ratio, 1-to-1 inductance ratio, and therefore a 1-to-1 impedance ratio. So I matched the 50 ohms of the signal source to the 50 ohm of the load. And just to keep things simple, I kept the transformer with an ideal coupling factor of 1. Now of course we can try out a more interesting example. So what I have here is the same signal source with the 1 volt amplitude and the 50 ohms of series impedance, but the load this time is 200 ohms. And to interconnect the two, I drawn up a transformer that has two inductors, which have a turns ratio of 1 to 2, which corresponds to an inductance ratio of 1 to 4, and an impedance ratio of 1 to 4. So 52 to 100 is equal to 1 to 4. And we can verify how well this works. First of all, the amplitude of the signal coming out of the signal source, 500 millivolt peak, so half that of the no load condition. And the power delivered to the load comes in peaks of 5 milliwatts. So we're getting the exact same thing as we did when we were driving the initial 50 ohm resistor. Now, another interesting thing to look at is what happens when you have multiple secondaries. So maybe you want to drive multiple loads at the same time. So starting off from a basic sample where we have a 50 ohm signal source driving a single 25 ohm load with the matching transformer, so we need an impedance ratio of 2 to 1, 50 ohms to 25, which corresponds to an inductance ratio of 2 to 1, or a turns ratio of square root of 2 to 1. And rather than driving a single 25 ohm load, we want to drive two 50 ohm loads. So the two loads in parallel correspond to 25. Well, we can achieve this using this setup. So we have a transformer with 3 windings that have the same inductances as before, so 200 on the primary and a couple 100s on the secondary, but this time we have two 50 ohm loads. So if we run this and check it, first of all, the signal coming out of the signal source, 500 millivolt peaks, so that's good. But now if we look at the power delivered to the load, we see we have 2.5 milliwatts. But that is not a problem, because we have two loads, both receiving 2.5 milliwatts, and we can simply work out what the sum of this is. So we can copy the expression of the power delivered to the second load, and simply add it to the power delivered to the first load. So we can let LT-Spice calculate the total power being delivered to the two loads, which is the 5 milliwatts. So again, everything is matched. Now, one final interesting case to show off is a different way of driving two loads without using a free inductor transformer. So of course you can use the previous version, but you can also pull it off using a single 2-winding transformer. So what I prepared here is a setup in which we have a 50 ohm signal source and two 25 ohm loads. And the signal source is driving the first load in series with the impedance matching transformer. So basically, the signal source is seeing the transformer plus the first load. And since the transformer is a 1-to-1 transformer, the load on the secondary of the transformer, which is again 25 ohms, is what's being seen on the primary. So the signal source sees the 25 ohms in series with the other 25 ohms, so 50 ohms in total. So we can quickly verify if this is working correctly. Again, the signal coming out of the signal source, 500 milliwatts. And if we look at the powers delivered to the two resistors, again 2.5 milliwatts, which added up result in the 5 milliwatts peak power. So you can go with 3 inductors or fewer, depending on your use case. It is important to mention, however, that this will only work if the loads are smaller than the initial signal source impedance. So you will not be able to drive higher loads with this method. With the previous method, with the free inductor transformer, you can drive any value of load. Now, as you may have noticed in the previous calculations and simulations, we didn't really care about the signal frequency. The only parameter linked to the impedance ratio was the turns ratio. And in an ideal simplified world, that is sort of true. But it's not in the real world. The actual inductance value and the various parasitics of the transformer play a key part in the actual frequency response of the circuit. You can't simply have a transformer with any number of turns and just respect the turns ratio. You have some other things to also consider. Now, I don't want to go into too much detail on this, since I covered this in an older video, but the equivalent model of the real transformer looks something like this. So right here in the middle, you have the ideal bit of the transformer, so this respects the turns to voltage to currents ratio, and then you have all these other things. So on the primary side, you have a resistor representing core losses and an inductor representing the magnetizing inductance. Then you have various losses. So for example, the primary side and secondary side series resistance. This represents the resistance of the wire. Then you have some uncoupled inductance on the primary and on the secondary side. So not all of the windings are perfectly coupled in the transformer. Part of them are uncoupled. And finally, you have some capacitances. So you have some parallel capacitance both on the primary and on the secondary side, and you have some interwinding capacitance that links the primary to the secondary. And based on the various values of all of these elements, you will have a specific frequency response and thus a specific transformer bandwidth. Other than the coupling factor, the main elements responsible for the bandwidth will be the load that is connected to the output of the transformer, the various coil inductances, and the parallel capacitances. So we can make a good approximation of the various corner frequencies, so the low side and the high side of the transformer, based on the final load that is connected and the inductance for the low side, and for the high side mainly the load that is connected and the various capacitances on the primary and on the secondary. Primary capacitance being multiplied by the inductance ratio. And this will determine the bandwidth in which the transformer has a flat response, and outside this we have a filtering effect, so high pass on the lower frequencies, low pass on the high frequencies. Now the best way to test this out in the simulator is by using an AC simulation. So a simulation that you perform between various frequencies to see how your impedance matching transformer will behave. So what I prepared here is a setup with a signal source that has an 800 ohm series resistance and the load that is only 8 ohms, so we have a 100:1 impedance ratio, and to interconnect the two, I prepared a transformer that has a 10:1 turns ratio or an 100:1 inductance ratio, so 1 millihenry and 10 microhenry. And if we look at the signal getting delivered to the load, we see that we have this high pass behavior, so at low frequencies very little signal gets delivered, and only after a specific point does the delivered signal amplitude flatten out. So we're getting our proper impedance matching and power delivery only when this flat portion of the curve is reached. Now we can move the whole graph to the left a bit by increasing the inductances. So I have this other setup in which we have the same 800 ohms on the signal source, same 8 ohm load, same turns ratio 10:1, but this time the inductance is 100 times bigger. And if we look at the delivered signal, this time we can see that we have the same flat portion, but the corner frequency has been moved much lower. So by increasing the inductance 100 times, we went down to decades. Now of course, just by adding the inductance of the various inductors, we're getting the high pass effect, but we're not getting a high frequency limitation. So to do that, we also need to add some parallel capacitance. So any coil will have some parallel capacitance. And if we add these elements in, then we see the true behavior of the transformer. We're getting a high pass effect at low frequencies because of the inductance, and we're getting a low pass effect at high frequencies because of the parallel capacitance. The key in getting a wide bandwidth is therefore very large inductors, but also very small parallel capacitance. To a certain extent, capacitance is linked to the number of turns. More turns means more capacitance, so to get both low capacitance obtained with few turns, but at the same time a large inductance, you will most definitely need a magnetic core providing magnetic permeability. Another thing to observe is that when you need wideband impedance matching, but you also need to obtain galvanic isolation in the signal path, especially at low frequencies, you will be using transformers. For example, in audio amplifiers built with vacuum tubes, you need some way to match the kilo-ohm level of the output impedance of the vacuum tube to the signal digit impedance level of the speaker. But other than this requirement, there is also the safety requirement. Vacuum tubes typically work with very high voltages, so in the range of hundreds of volts, and the speaker cables are sometimes accessible, so you want to keep things safe. So by using a transformer with isolated inductors, you can achieve both features. And as long as the various parasitic and constructive characteristics are kept in check, you can also get the wide bandwidth needed to transmit the full audio spectrum. Another interesting wideband application is digital data transmission, so square waves. Even though in a square wave you have portions of DC and portions of steep transitions, a square wave can be decomposed into a set of sine waves using a Fourier analysis. What this means is that if the various sine wave components are within the bandwidth of the transformer, you can send a square wave through the transformer and get the benefit not just of matching different impedances, but also getting galvanic isolation. Especially over long data transmission lines like Ethernet, you will see isolation transformers. And based on the cable impedance and the driver impedance, these can be one-to-one transformers or different ratios can be implemented. So we can again explore this behavior in a circuit simulator. So what I prepared here is, first off, a signal source, which is outputting a square wave. So if we just zoom in a bit, we can see that this is a 500 Hz square wave with a 1 volt amplitude. Now we can analyze its spectral content by looking at an FFT spectrum of this signal. We can see that this signal is formed from a fundamental frequency at 500 Hz and then various upper frequency multiples. So we should be able to transmit this signal through a transformer as long as we can transmit all of these various harmonics. So I took this signal source, made a copy of it, and I'm driving it through a one-to-one transformer that has quite large inductors, so 1 Henry on the input and on the output, and going into a 50 ohm load. So if we run this thing, we look at first of all at the signal coming out of the signal source. We can see that we only have an amplitude of 250 millivolts, but it's actually 500 millivolts because it's not referenced to 0, rather at minus 250. And if we look at the output, we see the exact same thing. So we see that our square wave has passed through our transformer. Now, since we're talking about AC signals, they will be referenced around 0. So that's why we're not getting the initial signal from 0 to 1 volt. First of all, we're getting half of it because we're matching the impedances, so 50 ohms on the signal source, 50 ohms on the load. We should only be getting half of the initial 1 volt, so half a volt. But because we're only transmitting the AC component, everything is referenced around 0 this time, so plus minus 250 millivolts. Now, if you don't need galvanic isolation, you can build a single inductor with a tap somewhere. So this is called an auto transformer. Although you're giving up the isolation, this provides an important benefit. Since part of the wire is common to both sides, you will be using less wire to build the thing compared to having separate inductors. And less wire means less resistance, and therefore a reduction in losses. But also from a manufacturing and an economical point of view, this will also mean a slight reduction in price. Now we can show this off by starting from a previous example. So what I have here in the upper side is a transformer matching the 50 ohms of the signal source to the 200 ohms of the load using isolated inductors, and in the bottom side I'm matching the same impedances, but this time using two inductors in series. Now from a turns point of view, in the upper transformer we have a 1:2 turns ratio, whereas in the bottom side we have two identical inductors. So the primary side sees a turns ratio of 1, whereas the secondary side sees a turns ratio of 2. Now even though the inductors seem to add up to only 200 microhenry on the secondary, because they are on the same core, their equivalent inductance will be higher, so the 400 microhenry that we had above. So we can test out if things are matched correctly. So on the upper side we have 500 millivolts coming out of the signal source, on the lower side we have exactly the same thing. And then from a power delivery point of view, on the upper side we have 5 milliwatts, on the lower side we have the exact same 5 milliwatts. So from a matching point of view, both circuits are equivalent. Now, since coupling factor is so important, one interesting constructive method is to wind multiple coils at the same time, so to have the turns from the inductors interlaced. So I looked at this a while ago. This coiling technique ensures the highest coupling factor in between the inductors, so it's a superior construction technique compared to keeping the coils separate. You will see schematic designs where you have multiple coils on a transformer interconnected, and these basically form an auto transformer with a specific turns ratio. So from a schematic point of view, it's the same thing as drawing a single inductor with a tap, but this specific drawing method is simply there to highlight the constructive characteristics behind it. Now, a key part of the use cases we looked at today was a high coupling factor. This is quite easy to achieve as long as the transformer has a continuous magnetic core. But that is not always the case. Especially in high power or high frequency applications, you will be going with an air core, since the magnetic core would either saturate or it simply does not provide adequate magnetic permeability. This brings us to an interesting problem. How do you get good energy or signal transmission when the coupling factor is poor? Well, that is a topic to explore for next time. But for now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Be sure to subscribe to be updated with all my latest videos, and see you next time. Bye bye.